Any suggestions? Okay, so we know it's our ideal value plus or minus 20%. But if you think about it, this ideal value, whatever it is here, represents 100%. So you're going to split that up. The minimum value is 100 minus 20%, correct? Which would be 80% of whatever that ideal value is. The maximum is going to be 100 plus 20%, or 120%. Which one do we have here? It says the lower end. So we have the minimum value. What we have there is representing 80%. So 80%, again, a percent is always out of 100, so it's 80 out of 100 equals, that represents the 80%, so that goes on top with the 80. And what we're looking for is the full amount. Remember, the 100 in our percent always represents either the full amount or the initial value. So that's what we're looking to find. We cross, multiply, and divide there. What are we going to get for this amount? Close. Stop by a zero. Decimal place. 63,000. Does that make sense? Okay. So out of your packet from yesterday, you guys have any questions on those homework questions? Any of those you want me to go over? Yeah. Okay, what do you have? Which packet's that on, the 12 or the 6? It's the 12?
Yeah, it's the 12.
To what page?
264.
Okay. So number 6? 13? Okay. The specified source voltage for a motor control center is 480 volts. I don't know if you guys discussed significant digits last semester or not. The reason they put that 0.0 on the end there is just significant digits. That's to show that voltage is measured to the nearest tenth of a volt. Not just the nearest volt, but the nearest tenth of a volt. And it still is closer to 480.0. Calculate the maximum and minimum values of load voltage across the motor when the measured source voltage plus or minus 5%. So what they're doing, they want you to calculate the actual range across the motor. The measured voltage, what you're getting off your meter, is this amount. And they're telling you to allow 4% off the specified voltage, that's off the 480, for a loss in your wire and loss in the system. So let's figure that out. What is 4% of the 480? $18.2? 19.2? 19.2 volts. So what that means, if I subtract that from that specified voltage, that would put me at 460.8 volts, which is lower than what we're getting for our operating voltage. So that's telling us that that's the specified voltage. It's actually operating at a higher voltage than that. Oops, I'm sorry. They actually are testing it at the motor, not at the load. So you want to find the minimum and maximum load values. So we're finding that 19.2 volt loss. Now we got, this is what's measured, is what our source is actually putting out. So we're going to look at this to find the actual range of what the actual output is. So 5% of 468.8, cross multiply and divide on that one, you're going to get what? So 3.44. Yeah. So that is 468.8 plus or minus 23.44 volts. But there is a loss of 19.2 volts. So there's two ways we could do this. We could either take this source here and find the minimum and maximum, and then subtract the 19.2 volt loss from each of those. Or the simpler way, now that we actually have this allowance here, this plus or minus here, we could just subtract that 19.2 volt loss from our source. Why couldn't we subtract that before we got this number? Because we had to have 5% of this to establish what that error really was. So we had to find the 5%, convert it from relative to an absolute before we subtract the loss. So I'm going to go ahead and subtract the 19.2 volts from my 468.8. So we're getting at the device, we're getting 449.6 volts plus or minus 23.44. And now we can add and subtract that to get our minimum and maximum. So our minimum is 426.16 volts to our maximum 473.04 volts. Does that make sense? So really the only purpose for giving you that 480 volt specified is you needed that to determine what your loss in the wire was. After that, the tested voltage is what applies to that. Any others you want me to go over? Okay. So what we want to talk about today is we want to talk about work and efficiency. Work or energy is the kind of tightly correlated with power. Power is the ability to do work in a given amount of time. So all systems, because they lack perfection, I should say, have some sort of an energy loss or a power loss. Plug that in. So the work done by a system, think of the efficiency. You have the work that's put into the system that is equal to the work that's put out of a system plus whatever is wasted. Now, if you look at a mechanical system, like, I don't know, pushing a wagon or whatever, that waste is usually friction. In an electrical system, that's resistance, heat, energy. It's work that's converted to some other form that's not useful to us. A more typical way of stating this is in terms of efficiency. And efficiency, rather than having this term in here for waste, just focuses on the work that comes out of the system and the work that's put into the system. So the symbol for efficiency is actually the Greek letter zeta. And it looks almost like a cursive Z. It is the work that comes out of a system divided by the work that's put into the system. And that's as a decimal, or it can be converted into a percent, however you prefer to do it. So let's say we have a system that has 3.2 kilojoules of work put in, and the work that comes out of the system, or the useful work that comes out, is 3.0 kilojoules. That would make the efficiency of that system, which number is going to go on top? (3.2 or 3.0? Well, the work out goes on top. That's the 3.0. Now, at the first stage, I do leave the units on it usually. The work in is the 3.2 kilojoules. The main reason is I want to make sure that both of these are being expressed in the same terms. So now that those are the same units, I can cancel them out. 3.0 over 3.2 is going to give me 0.9375. So I have an efficiency of 0.9375, or if I want to convert that to a percent, move that decimal over 2 spots, 93.75% efficiency. Now, a lot of times, rather than measuring the actual work, we're not used to measuring electrical power in joules. What we measure is the power. So you can adjust, and when we're dealing with electricity, the efficiency is often the power output compared to the power input. So let's say that you have a device that has an input power, 360 watts, and an output power, 300 watts. How are we going to calculate the efficiency? Which one of those is going to go on top? The output, which is the 300. Right? What's going to go on bottom then, of course, is the 360. The watts cancel out. 300 divided by 360 is 0.8333, or 83.33%. Not always going to be given to you in nice, simple terms like that, where we give you the power in and the power out. I might give you that we have an appliance draws 8 amps on a 110 volt circuit. Produces 750 watts. So it might be a microwave. Like a lot of your microwaves, I know 750 watts is a very, very weak microwave. But some sort of appliance like that, it's rated to 750 watts. It draws 8 amps off of a 110 volt circuit. What it produces, its production rating, is the power out. That is its output. How do you find the power input? Amps times volts. Very good. 8 amps times 110 volts, 880 watts. So my efficiency here is 750 over 880. So if I divide that out, 85.23 or 0.8523, or as a percent, 85.23%. Any questions so far? Well, when we are dealing with electrical power, a lot of our electric motors and stuff are rated, might be rated as 2.5 horsepower or whatever. For electrical power, 1 horsepower is equivalent to 746 watts. So if we have a motor that is rated 2.5 horsepower. On a 110 volt circuit, it is drawing 25 amps. How do we find its efficiency? Oops. Well, this is going to be the power out here. It's rated at 2.5 horsepower. So assuming it's achieving its power rating, that's its output. How am I going to change 2.5 horsepower into watts? Well, I'm given this equivalency here. 1 horsepower equals 746 watts. Do you guys remember how to do measurement conversions? Horsepower is going to go on bottom. Perfect. The watts go on top. So yes, the horsepower cross cancels out. 2.5 times 746, which is 1865. You are correct. So 1,865 watts, or 1.865 kilowatts if you wanted to change it. We're just going to leave it like that for now. What's the input power? I'll turn it. $25 amps times 2750. There you go. 25 amps times 110 volts. So 25 or 2750 watts. So our efficiency, the 1865 that we get for output at 2.5 horsepower over the 2750 input, .6782 or 67.82% efficiency. Any questions so far? So if you have a multi-step system, where you have several devices hooked together, to get the system efficiency, so this might be, if you're looking at this, maybe look at like a satellite system. This might be the receiver. This might be a splitter. And this might actually be the box at the TV that has to convert the signal for the television. Let's say your receiver is 92% efficient. The splitter, obviously, you're sending the signal in 2 different directions. Let's say that is 80% efficient, or you're going to have an 80% transmission. And your box over here is going to be 98% efficient. To get the system efficiency here, you convert those percents to decimals. And you can simply multiply your efficiencies together. So 0.92 times 0.8 times 0.98 give us 0.72128. So the overall system efficiency from the signal at the receiver to what goes to your set, 72.128%. What do you think? Not terrible? So here's the thing. Let's say that we have 3 devices. You're going to kind of chain them together. I know this is a very inefficient way to string them together. Let's say you have 3 boxes you're going to hook up for a home entertainment system. And rather than doing a splitter and going off to each of them individually, you're going to go into the first one, and then from the output of the first one, you're going to go to the second one, and do the same and get to the third one. So obviously the signal is going to be weakest at which one? The last one. Because each of these, as you go through it, is going to have a signal loss. Let's say that of these devices, one of them, you put them on the bench. They're all three identical devices. You put them on the bench and you test them. One of them tests to be 96% efficient. One is 93%, and one is 91%. Does it make a difference? Of course, this is going to be put into a television set as well. We'll just label that as output. Does it make a difference which one you put where? Let me word the question a little more specifically. Does it make a difference to whatever this output is, to what the signal level here is? It shouldn't. Very good. It doesn't matter what order I put them in, because even if I put the high efficiency one first, if I multiply those together, what do I get? There we get 0.812448. Or 81.2448. If I rearrange them and put them in a different order, I'm still multiplying the same numbers together. I'm going to get the same result. So my signal level here at that final output is going to be the same no matter what order I put them in. So does it matter what order I put them in? It would seem to say no, but the real answer is yes. Why?
One of those would be an amplifier or something.
If there's an amplifier along the way, I guess that might be a consideration.
No, because you're losing a certain amount of signal there, and you're taking that percent of that signal from the next one. So if you start with a bigger signal, taking away more.
Yeah, exactly. What it is you're at the very least you're passing the strongest signal possible on to the second device. The last device, it won't make a difference, but the signal level that goes here will be stronger if you put the more efficient one first. Does that make sense? So you're still getting a stronger signal at each step along the way. At the very end, your signal strength is going to be the same no matter what, but you're getting a stronger signal at the intermediate steps. Okay, so we're working out of your 12 packet still. On the 12 packet, pages 271 to 272, problems 1 through 13 deal with this efficiency. Let you guys have the last 7 minutes here to get started on those or finish up your quizzes if you need to.